Welcome to my series, Basic Mechanics, A Critical Look. This is lecture number 8. Now let us recapitulate that we had already been talking over the last few lectures about the application of Newton's laws to a system of particles. And in particular, what we had shown is the following. That if you have a system of capital N particles with masses m1, m2, m3, etc., with position vectors with respect to an inertial observer, r1, r2, r3, etc. again, respectively, then the following holds. If you multiplied each one of the masses of the particles with their corresponding accelerations and summed up the whole thing, this result, sigma I going from 1 to n of mi d2 ri dt2, would be exactly equal to the net external force acting on the system, which we have denoted by F external. Now, over the last couple of lectures, we have talked about the concept of the center of mass which follows from this. This actually follows by rewriting the left-hand side here as capital M, the total mass of the system, into d2 capital R dt2, the acceleration of a specific point whose position vector is given by capital R, and that is equal, this mass times acceleration is equal to the net external force. Here, as we have said, capital M is the sum of all the masses of the particles making up the system, and R vector is a weighted average of the position vector of the individual particles. Here the weighting is done essentially by the mass of the ith particle. So you get sigma mi ri in the numerator and sum of mi, of course the total mass, in the denominator. Now this special point is, as we have already mentioned, called the center of mass. This is a point that moves just like a particle whose mass equals the total mass of the system and on which the net external force is acting in totality. In other words, if you had a fictitious particle whose mass was exactly equal to the total mass of the system and on which we had assumed that all the external forces were acting, it would move exactly in the same way as the center of mass would. An immediate corollary of this is the following. If there is no net external force on a system, then its center of mass behaves like a free particle. That is, it stays stationary if it was stationary at the beginning, or if it were moving, it would keep on moving with uniform velocity. Now we had seen a problem, a very standard problem based on this idea, near the end of the 6th lecture of this series. In the previous lecture, the 7th one, we had actually seen how trying to make this problem of a boatman crossing from one end of a boat to another a bit more realistic leads to rather surprising results and some rather non-trivial mathematical concepts. Now in today's lecture, we are going to take a look at yet another way of rewriting the left-hand side of our equation. Remember, the equation that we are dealing with is this one, which is derived using both Newton's second and third laws. And of course, because we are assuming Newton's second law works, we have already assumed that the first law does too. That is, that the observer is inertial. So now, let's try to figure out another way of rewriting the left-hand side. For this, let us take a look at this term, mass of the ith particle into the acceleration of the ith particle. Since the mass of the ith particle does not change with time, we can simply rewrite this as ddt of mi dri dt, and that leads to a very well-known result, that this term is the rate of change of pi. Pi, mi times vi or mi times dri dt, is the momentum of the ith particle. So by plugging this in the sum on the left-hand side, we see that the left-hand side essentially becomes sum from I equals 1 to n of dpi dt, and we can of course sum up first and then do the derivative, so that this expression is exactly equal to ddt, rate of change with time, of the sum of all the momenta of each and every particle of the system. And if you call this sum the net momentum of the system, capital P, then the left-hand side of our equation essentially becomes rate of change of the total momentum, capital P. So plugging this back in our equation gives us another version of Newton's second law for a system of particles. In fact, this is the one which is usually called Newton's second law for a system of particles. Rate at which the net momentum of a system changes with time is equal to the net external force. An immediate corollary of this is a very, very important law, which is actually important even beyond classical mechanics, even beyond the region where Newton's laws are applicable. The law of conservation of momentum still holds sway. In our situation, that is, in the Newtonian mechanics case, it simply means the following. If there is no net external force on a system, that is, if F external is 0, then its net momentum is conserved in time. So, if you have a system of particles on which there are forces, but these forces may be internal only, or there are external forces which balance each other out, then the net momentum of this system, if the sum total of all the individual momenta, will not change. Note that although stated for a system of particles, we can also invoke this for a single point particle. But however, if we do this for a single point particle, it's really not going to be very interesting, because for one particle, this law is just the first law of motion. After all, if you have only one particle, then the net momentum of your system is exactly the same as the momentum of that one particle. And all forces, of course, are external now. So, our law simply becomes rate at which the momentum of a single particle changes is equal to the net external force. And in particular, if there is no net external force, the momentum doesn't change. But that's nothing but Newton's first law. Right? Because if F external, which is F, is 0, then mv is constant, which means v is constant. A point particle on which no external force acts maintains a constant velocity, stays at rest if it were initially at rest, or moves with uniform speed along a straight line. The law of conservation of momentum really comes on its own and acquires a huge deal of importance if more than one particle is involved. In order to see a more non-trivial application of this law of conservation of momentum, let us consider the simplest extension beyond a single particle. Let's talk about two particles which collide with each other. So the picture that we are looking at is the following. Before the collision, you have two particles with masses m1 and m2 respectively, and the velocities are u1 and u2 vectors. They collide with each other, and after collision, the first particle bounces off with a velocity v1, the second particle bounces off with a velocity v2. All this, of course, is being observed from the point of view of an inertial observer who measures all of these velocities u1, u2 before the collision, v1, v2 after the collision. Now, net momentum of the system of two particles before the collision is m1 u1 plus m2 u2. Whereas the net momentum after the collision is m1 v1 plus m2 v2. We are assuming here that the particles remain intact during the collision. They don't break open or merge or anything like this. If they did, then the masses would, of course, have to be altered in accordance to that. But irrespective of whether the particles maintain integrity or break up or merge together, what remains true is that as long as there is no external force on the system, the net momentum is the same. So you have this vector relationship m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. Or in the more general situation, you have this simple rule that net momentum before collision is equal to net momentum after collision. Now, this law of conservation of linear momentum is one of the cornerstones of physics. Its applications are immense, and you are going to see more and more of those applications as time goes by. Apart from that, however, it's also very important for a physics student for the simple reason that many rather complicated problems can be simplified and solved rather easily if you use this particular principle, which actually makes life a lot easier for a student who has assignments or exam questions to handle. Now, one such typical problem which comes in many exams or in many problem sets is the following. I'm not going to go into the details of the problem. I'm pretty sure all of you know these pretty well. The basic idea is that a ball is dropped from the top of a tall tower. A second ball is thrown upwards from the bottom. They hit, being aimed rather nicely, and then they stick together upon collision. And of course, after that, the question would be something like how much is the velocity of the particle after collision, the combined particle that is, or how long after the second ball was thrown does the combined particle reach the ground, or many such variants of this. But the basic thing that you have to do is simple. You have to figure out the velocities of each of these two balls at the instant when they collided, and then use conservation of momentum. Since they're sticking together, the mass of the combined particle is now, or rather the combined system, is now the total mass of the two particles, or two balls, and you have to divide the total momentum of the system, which remember could involve a subtraction because these are vectors we are dealing with. You have to worry about whether the momenta are in the same direction or not. And using that, you would find out the velocity of the particle after collision and then use that to calculate various other things. I am not really interested in the details of the problem at this stage, but at a rather important conceptual issue that is often skirted around when we talk about this. And this conceptual issue is simply the following. This problem is not one in which there is no external force. After all, you determine the velocities of the two balls at their moment of impact by making use of the fact that they are both acted upon by the force of gravity. And these two forces of gravity acting on the two balls definitely don't cancel each other out. If you were to add them together, they would just simply add up in strength, being in the same direction. So, the conceptual question that should be addressed here is simply this. Since there is an external force on the system, are we at all justified in using the conservation of momentum, which remember is valid only when there is no net external force? So the conceptual issue here is the following. Are we at all justified in using the law of conservation of momentum, as we do use in this case, to determine the velocity of the combined system after the collision, in this situation where there are external forces? In order to understand why this is a justifiable thing to do, we need to take a look at a related concept, the concept of an impulse. An impulse is something which a force produces. Actually, the net change in momentum caused by a force. That is the impulse of a force. Since rate of change of momentum, even for a single point particle, is given by the force, the change in momentum this force causes is simply given by delta of p vector. The change is the integral of f vector dt from time t1 to t2, where t1 to t2 is the interval over which the force acts. And if the force is more or less a constant during the interval, you can drag it out of this integration and you will get f vector times the time interval. So, the impulse produced by a force is essentially its size times the time interval over which it acts. Now, The special thing about collisions is that a collision lasts for too short a time for gravity or similar forces to produce significant impulse. The force of gravity may be rather large or small, but the time during which a collision acts is really a tiny fraction of a second, during which time the impulse produced by gravity or similar forces would be insignificantly small. So, in this situation, you do have an external force. You do have the force of gravity, and that does change the momentum a bit. But if you are connecting the momenta just before and just after the collision, the time interval is too short for gravity to make much of a difference. Now, having said that, we now get to puzzle number 2. And the puzzle number 2 is simply this. Instead of taking the two balls which collide together as our system and using conservation of momentum there, couldn't we have taken just a single ball as a system? Remember, as we have emphasized over and over again when we talked about a system of particles, exactly which point particles make up your system and which ones are external to it is a matter of definition. You can choose your system as is convenient for you. If you take the two-ball system in this problem, you are going to have conservation of momentum. The external force is present in this case and will of course change the momentum in the long run, but in the very short interval during which the collision takes place, the external force produces no effect. But I am equally within my rights to take a single ball as my system. And then something strange happens. The momentum of a single ball definitely changes before and after a collision. The question would be, how can this happen if, as we have just argued, the time duration over which the collision takes place is so very short? And the answer, of course, lies in the fact that now we have a new external force. When we took two balls together as our system, the force that one ball exerts on another was an internal force. In fact, each ball produced a force on the other one, and these forces being equal and opposite, being action-reaction forces, cancelled out in the overall net force summation. But now this will no longer happen. The force which the other ball exerts on the ball which we are considering our system is now an external force. So, in addition to gravity, which was an external force we had even previously, have one more external force. But what makes the thing so different is that this external force is huge. This force is so huge that it can cause a finite change in momentum even in the short duration over which a collision takes place. And forces of this kind, which can cause a change in momentum despite acting for a very, very short time, these are exactly what we call impulsive forces. Note that all forces have impulse. Roughly, that force multiplied by the time interval over which it acts. An impulsive force is one in which delta t is very, very tiny, but F has a huge magnitude, so F delta t is substantial. So, a substantial change in momentum despite acting for a very short period of time. This explains why the momentum of a single ball gets to change during the collision. You now have to treat the force exerted by the other ball as an external force, and that force happens to be impulsive. So, we have managed to explain how the momentum of a single ball manages to change during a collision, which is so short-lived that the momentum of the overall system does not change. It all has to do with the fact that the force which one ball exerts on the other is so huge. But this begs the question, why is this force so huge? In order to understand that, let's just take a moment to understand why one ball exerts a force on the other in the first place. So imagine two balls coming head on and hitting each other. Now, if the balls were not exerting forces on each other, then their velocities would simply not change and they would just go through each other. Of course, here, when I say the velocity does not change, I mean in the very short duration during which they are in contact. After all, the force of gravity is very much there, and that will definitely change the velocity of the two balls. But we are not talking of that right now. Now, if the two balls were to carry on with their original velocities, they would simply have no option but to go through each other. Of course, that doesn't happen. What happens is that each ball deforms the other one in a very, very huge way. As a result of this huge deformation, which is caused very, very rapidly, you have huge restoring force. That's the response to this deformation. And because the deformation is pretty huge, so is the restoring force. That exactly is the reason why you see an extremely large force cropping up here. To back up what I've said right now, I scoured the internet looking for fast motion capture camera pictures of two balls hitting each other. Maybe I did not look hard enough, but I didn't really find such pictures that would suit my purpose. Instead, I'm going to show you pictures of a tennis ball dropped on a hard floor. The basic idea is the same here, except that the deformation of the ball here would be a bit smaller because the floor is really not moving through it. It's only the ball which is moving through the floor, or at least trying to. And of course, here the ball is the one which would apparently deform. The floor, being much more rigid, also deforms, but we will not be able to see the deformation, at least so obviously. So let's see a few pictures which illustrates that. On the left, you have the ball just before it hits the ground. A nice spherical picture. Here it has just hit the ground. You have a bit of flattening that's starting. That's a deformation that has just started. In the third picture, the ball has tried to go through the floor a lot by now. Of course, the floor doesn't give way. The ball deforms quite a lot. The fourth picture, the ball has deformed a lot more. Now, I could, of course, keep on adding picture after picture of this, showing how great this deformation is. And after that, once the restoring force has managed to produce enough of a change in momentum to reverse the motion of the ball, how this deformation gets slowly released and the ball regains its original shape once it has bounced back completely. But I will leave the rest of the pictures to your imagination. You can of course find the video from which I took these successive screenshots by doing a quick search on the net. The point I'm trying to make is simply this. Huge deformations caused by colliding objects produces huge restoring forces. And that is why you have sufficient impulse to change the momentum drastically, despite the fact that the collision occurs over a very short time. Now that we have addressed these puzzles concerning collisions, let me end today's talk with another puzzle. This is the puzzle of the gun that refused to fire. Now, the background of this puzzle is a problem that again is very familiar to all of you. The problem is usually stated in the following terms. A bullet of mass small m is fired from a stationary gun of mass capital M. If the velocity of the bullet is u, of course after it has been fired, what is the speed with which the gun recoils? Now, I'm pretty sure all of you know how to use the conservation of momentum to calculate the recoil velocity of the gun, and those of you who have actually fired rifles or pistols of some kind during NCC training or some other event, or even while trying to burst balloons in a fair, would have actually felt the recoil velocity. But let us now try to analyze this from the point of view of an observer who is fixed to the gun. Maybe a fly who is sitting on the barrel. Now initially, both the gun and the bullet are at rest with respect to this observer. So velocity of the gun and the velocity of the bullet is 0. Here, of course, everything is going to happen in one dimension, so we are not really treating the vector nature of the velocity. Especially, we are just talking about the speeds here, with, of course, the sign taken into account. Now, since the velocity of the gun and velocity of the bullet are both 0, the net initial momentum of the gun plus bullet system is 0. Now, when the gun fires, there are of course internal forces produced by the blasting powder or whatever makes the bullet fire. But all of this is internal to the gun plus bullet system. There is no external force. Or you might argue that there are external forces like gravity at play here. But once again, the explosion which causes the bullet to fire takes place in a very, very short interval of time, during which non-impulsive forces such as gravity hardly manage to change the momentum. So we can use conservation of momentum. Now, according to the law of conservation of momentum, after the bullet is fired, net final momentum must be 0. But remember, the gun is fixed to the observer. So when the bullet is fired, the gun stays stationary with respect to our observer. So momentum of the gun with respect to this observer is 0. Net final momentum being 0 implies that the momentum of the bullet also must be 0 with respect to the observer. So no matter what the ground-based observer may be saying about this, according to conservation of momentum applied to an observer fixed to the barrel of the gun, the bullet must have 0 velocity with respect to the gun, so the bullet refuses to fire at all. Now, as you all know, this cannot be correct. After all, the problem of gun violence cannot be this easy to get rid of. I would like you to think about exactly what is going wrong with the arguments that we have used here. Let me just repeat once again that all we have used so far is simply the fact that initially both gun and bullet were stationary with respect to the observer, leading to a net initial momentum of 0. Then we have used the conservation of momentum, which leads to net final momentum being 0. And since the gun is obviously stationary with respect to our observer, the momentum of the gun has to be 0 both before and after the firing, and therefore the momentum of the bullet after the firing must also be 0. This is the totality of our argument. There must, of course, be something wrong with this argument, because as we all know, guns do fire in real life, bullets do emerge with a high velocity and cause a lot of damage. I would urge you to think about this problem and try to figure out for yourself exactly where our argument goes wrong. That is the puzzle with which I'm going to end today's lecture. See you next time.